Hello, everyone. Hi, or howdy, I guess. I got the hat. My name is Richard Schneeman. You are in the talk for the life-changing magic of tidying up active record allocations. On the internet, I go by Schneems just about everywhere. Schneems.com, Schneems on Twitter, Schneems on GitHub. It's not a really common thing. So some people who know me know that I love Ruby. Some people who really know me know that I am actually married to Ruby. This is my wife. We have 2 beautiful children. We also have a couple of dogs. So this is one of my dogs. His full name is Hans Peter von Wolf V. He is actually the 5th Hans Peter von Wolf. My family has had this tradition, and they're not all genetically related, but they all are black and tan wiener dogs. It's a bit of a mouthful, so whenever we are screaming out the door, we don't say that full name. Instead, we just call him Cinco. He likes sleeping with his tongue hanging out. I don't know why. I work for a small startup based out of San Francisco. It's called Heroku. And we have a booth at RailsConf. So in fact, we've had a booth at RailsConf for the past 7 years since I first joined. And since you like performance, or you probably wouldn't be here, there's a talk given by another engineer, Gabe, on multi-database in Rails. Unfortunately, it was yesterday, so you're going to have to check that out on Confreaks, but I highly recommend it. I got to see a sneak preview, and it was pretty good. You might be wondering, what's up with these fancy gloves? I've got fancy gloves. It's not because it's cold here. It's because that I heard that a lot of companies are really interested in ninja developers. All right. So in actuality, I hurt my hands, and you might want to say, well, how did you hurt your hands? And I will tell you, extreme programming. Just too agile, y'all. Okay, it was actually regular programming, just a lot of it, and my physical therapist says it's going to take a couple of months to heal up. In the meantime, I've actually learned I'm back at work, and I've learned how to completely drive my computer using my voice and my eyes. So here's a semi-old video showing the process, if you're kind of interested, and I am a little bit faster now. Click. Sun, cap, harp, near, each. Each. It works a little better. I got a microphone and all that. So you might be wondering how I was able to make such amazing slides and such an amazing presentation without actually being able to touch a keyboard. And the answer is I wasn't. So for that, I would like to, for everyone to give a hand to my hands. Caleb Thompson. Instead of working on his part of the talk, we spent the last week pairing and building out the deck. So yeah, I'm super grateful. Yeah, I was originally just distraught, and I'm like, oh, I'm gonna have to cancel my talk. And then Caleb stepped up, and I think the deck is way better than anything I would have come up with. So, okay, all right. Who knows who this is? Okay, this is Marie Kondo. She's a world-famous organizing expert. She has books. We actually got her manga copy of the Tidying Up. It's actually really good. She's a best-selling author and has a Netflix show. I wanted to show you a clip of Marie that she's currently working on for a new show. So a lot of people don't know this, but she's actually also a programmer. And so yeah, here's a little clip.
She looks excited. I'm so excited because I love
object allocations. Object allocations.
Oh, I want things to be more simple. I don't know how to fix it.
With the baby,
object allocations.
It's going to be more chaos.
Oh my gosh, we have too much stuff.
Yeah, tidying up active record allocations. I think it's going to be big. A lot of mass appeal. Better than Defenders anyway. I mean, come on. So sadly, Marie couldn't be here with us today, but we have the next best thing. I would like to introduce you to her pet rabbit.
こんにちは、皆さん、ようこそ。私はコンハレ。英語でハレはウサギって意味なんだ。ウサギはどんどん早く進むのが大好き。
I don't think everybody speaks
Hello,
English.
And
There we go.
welcome everyone. My name is Kon Hare. In English, Hare means rabbit. Rabbit loves to go really fast. I love colors, so I love Ruby. I also love performance. Today, you're here to hear the Kon Hare method of tidying your Ruby applications.
That's great. Can you tell us what that method is?
First, take all of your object allocations and put them in a pile where you can see them. Next, consider each one. Does it sparks joy? Finally, keep only the object that sparks joy.
Great. How do I know if something sparks joy?
If an object is very useful and keeps your code clean, and it's not causing performance problem, then it sparks joy. If an object is absolutely necessary and removing it from your code causes it to crash, then it sparks joy.
Yeah, that last one's kind of like a technical correctness technicality. It's like, I hate this object, but it's seg fault.
When we put all the objects in front of us, it will help to determine which ones we can consider getting rid of.
All right, okay, thank you very much. I see where you're going, and that's all a great point. So to put our objects on a pile, we're going to be using two tools, the memory profiler and derailed benchmarks. First, though, a little quiz time. Get you warmed up. Here is a benchmark of two methods. They do the exact same thing in two different ways. Both of them determine which is the larger of two inputs. Take a look at this code. It allocates an array in order to perform a comparison on two inputs. This other code is just going to perform a comparison on two inputs. Now, which of these do you think is faster? Do you think the array version is faster? Okay, I saw a hand go up. What about the comparison version? All right, okay, yeah. So I will tell you the comparison version is faster, but does anybody know how much faster? Shout out a number. 17 times. Anybody else? 3, okay. Did somebody say pi? Was that a? Okay. In fact, it is, doing the comparison with our direct logic runs about twice as fast as doing it with the array allocation. And I don't know, for me, they're semantically doing exactly the same thing. So to have such a dramatic performance difference between the two is, pretty stark. In general, touching memory is going to be slower than performing calculations. And this is not just true in Ruby. This is also true of just about every programming language. Even in C, it's like a mantra of like malloc is slow, don't malloc, or it's like only malloc a few times if you have to. Since we know that Ruby allocations are slow, and we've seen at least one case where we can write the exact same logic and perform fewer allocations, we can optimize by removing those allocations at the Ruby level. And that way, if a program uses fewer objects, then it's going to run faster. Ruby is also an object-heavy language. In this example, we are returning 2 outputs as opposed to just 1. And even though there's no array in here, thing.call doesn't produce array, first is not an array, last is not an array, in order for Ruby to run this code, behind the scenes, it actually allocates an array. And so, they're using objects and allocating objects even when we are not doing so directly. If we find where we're allocating a ton of objects, then that is going to lead us to potential hotspots that we can optimize. One thing I want to mention before we really get started is that not all object allocations are created equal, and some take longer than others. So in general, I ignore the number of objects, and instead I look at the amount of memory. I find this to be a better technique. Just disclaimer. my personal opinion. And also, while not a totally perfect metric, I find that the percentage of objects decreased roughly translates to the performance percentage improvement. So if I can decrease the application by like 5% objects, then roughly I can make it faster by about 5%. It is just kind of back of the napkin math, so you will always have to go back and double check yourself, because oftentimes in order to do that you have to add in additional comparisons, and your comparisons might actually eat up all of that performance saving. The really neat thing about this is that bytes reduced is a consistent metric. Typically, whenever you are doing performance work, you constantly have to benchmark. Make a change, benchmark. Make a change, benchmark. And the problem with traditional benchmarking, with running timings, is that they're inconsistent. You get a high variance. You have to run it over and over and over again. You know, you wouldn't just benchmark your method once. You have to benchmark your method 10,000 times to see, on average, is it slower or is it faster? So with this method, all we have to do is run it once before and once after. If you shaved off 5% of object allocations, it's going to be really, really consistent. Now, again, we do want to remember that it's only shorthand, and we always are going to have to go back and rerun those actual timing performance benchmarks. We can't just take it at face value. So,
Excuse me? Weren't you supposed to be telling people how to get all their objects into one place so we can use a Konghare method?
okay, got a little off the rails there, and that's an excellent point. So let's take a look at that right now.
Okay, be back in the hub.
All right. Come on, be back in a hop, people. Thank you. So the memory profiler gem is going to allow us to take all the applications in our program and view them. Behind the scenes, this is a nice wrapper for the object space allocation tracing. If you're trying to profile a Rails application, then you can use the derailed benchmarks gem. This is a gem that I wrote, and it will let you hit an endpoint in your application from the CLI. The benefit of this is that you don't actually have to start your server and refresh it and like kill it and like load a page and click a button and do this other thing. Like one CLI command and like you get benchmark results. And it saves me a lot of time, which is why I wrote it. So today we're going to look at a real-world case study of these tools, and we're going to be using an open source application, a Rails application that I run and maintain called Code Triage. First, though, I do need a little introduction.
Dun 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 dun.
Thank you, Aaron. I call this section inadequate record. If you pause long enough on stage, then people clap and laugh. Okay, so first we're going to run derailed against a real-life application, which is Code Triage, and this is going to give us a pile of memory allocations. Okay, so that's a pretty huge pile, and not all of it, actually. That's just as far as Keynote would let us scroll up. The output is going to show most of the memory allocations from top to bottom, and I start by looking at each file in that order. In this case, we've already looked at several, or I've already looked at several, and I'm going to show you the process of how I do this. Just I'm going to skip to one that's actually interesting for you. Once I pick the file, then I need to zoom in and get more information. To do this, we can use the exact same command before, but now we need to tell Memory Profiler and Derailed to only focus on a single file. Here's the new output when we're filtering by that single file. You can see it's much cleaner now, and it looks like the majority of allocations are coming from line 270 of the attributes.rb file in active record. Let's figure out what that does. Open that file. Oh, that worked. Here is our problem line number. Let's look at it and figure out what it does, why it exists. So it's inside of the respond to method in active record, and respond to needs to return whenever we have a method on that object. And because active record is backed by a database, it needs to say, hey, what columns are in this table, so that it knows what methods are available on that object. And in order to do that, it needs a string. So typically, when you call respond to, you pass in a symbol. But because of the way active record is storing the column names in the back end, it needs to convert that symbol to a string, and that's where our allocation is coming in. And then we're calling respond to a lot. So as a result, it's allocating a lot of strings. Once we have that string, then we iterate over each of the column names, and we see if one of them matches the string that got passed in. And then once we have that, then we turn around and check if the actual object we are using has that attribute. It's kind of a separate API. All right. Does this object allocation spark joy? How do you feel about it? All right. OK, it's in use, so it's useful. It's doing a lot of allocations, so not very performant. It does help our code, or does it help our code to be cleaner? Yeah, I don't know. Is it absolutely necessary? OK, good question. We don't really know yet. Let's find out and see if we can refactor this code while maintaining correctness. Looking at the code, the name variable must be a string because the database columns are stored as strings. So we have to make a comparison, or we have to make a conversion, but maybe we can make it somewhere else. My hypothesis is that instead we can find a way to perform the column check with a symbol directly. To me, this allocation does not spark joy, so let's just throw it away. Throw it in the trash, stomp on it, get rid of it. We never want to allocate a string. Let's get rid of that code, and...
Wait! You're forgetting something.
Yeah?
You must honor this code before you get rid of it.
OK. That is true. This code has been in hundreds of thousands of production applications. It's served us very, very well. Even though it doesn't bring joy right at this moment, I think we should respect it. So thank you, code. Now we can get rid of it. Unfortunately, if that's all we did, then all of our applications would break. So we also have to figure out a way to convert our symbol to a string without allocating. To do that, we can introduce a hash. The column names, or the keys of this hash will be our column names as a symbol. And the return value can be the column names as a string. This is our old code. We can replace it with this. We can use the hash to both check for if the column exists, and then it returns a string, which we can then use for return has attribute. We also get a little bonus performance bump, because in this case, a hash lookup is faster than iterating over every column in that table. And one other thing to note is that calling to underscore something generally means an allocation or a type conversion. In this case, the most common thing that we're going to be doing is passing in a symbol. So therefore, calling to sim on a symbol is just going to return a symbol, no allocation. We're good to go. And so that's pretty much it. How much did that help? The patch reduces overall allocations at the web request level. So a request is coming in, stuff is happening and being served, by about 1% of total memory for code triage. But is it faster? On average, it caused render time to be about 1.01x faster, which roughly matches the 1% that we saw. So, I mean, that's it. I think we're pretty much done and ready to move on.
You are so lazy. You're not done yet. You have shown that it is faster, but you have not shown that these results are statistically significant. It is time to teach them the tease test.
All right. OK. So who knows what this is? If you said that this is a T, congratulations, you passed the t-test.
You know what I'm talking about. Show them the benchmarks.
All right, OK. So here's some example code and an example of how numbers can lie. We've got two objects, an array and a string. We can take a look at Memory Profiler, and it will tell us that if we duplicate each object, both of them are the same size in memory, 40 bytes, which is the standard for an object in Ruby. Pop quiz, which is going to be faster, duplicating that array or duplicating the string? That was actually more of a rhetorical question. You don't have to answer. So as you can see, duplicating the array is actually faster. And then we can, what? Duplicating the string is actually faster. OK, scratch what I said about the array. So with this information, we can, so it looks like all of them are roughly about the same. I could lie and cherry pick and just pick one and be like, hey, look, I ran a benchmark. The benchmark told me it's faster. But that would be lying with numbers. Instead, we can use students' t-test to determine if our numbers are statistically significant or not, whether this benchmark actually is showing us a difference or if the difference is just caused by randomness. So students' t-test was introduced in 1908 by William Seeley Gossett, who worked for Guinness. That was very dramatic. Why is it t-test if Gossett created it? Well, I'm sure this is going great in the recording. Guinness wouldn't allow any of its employees to publish their findings because they were worried if they said, oh, this is what Guinness is using, then we'll use it too. And they were very worried about that. So instead, Gossett published under a pseudonym of Student, which is, I don't know, not very creative, if you ask me. What exactly was Guinness doing with this information? The problem is that they were trying to solve is that the quality of their product depends on their quality of their ingredients. And different suppliers' quality might vary, or different batches might vary. And while they could take a sample from here and a sample from here and compare it to a sample from here and a sample from here, how did they know that they weren't actually just comparing randomness and that the values were significant? And that's where students' t-test comes in. And so,
hey, this history lesson is interesting and all, but let's get back to object allocations.
OK. Fair. So in my work, I used a very advanced statistical programming tool set. It helps you to Excel. And there's a function that generates a t-test for you. If the result is under a certain threshold, then it means the change likely wasn't a result of just random chance. 0.05 is typically a pretty good number.
Well, was your change statistically significant?
Yeah, so it got merged in.
Cool, but 1.01 times faster isn't much to brag about. You'd need to get 10 pull requests merged into make the program 1.1 times faster.
All right, that's true, but it is a 1.01 times speed up at the total web request level. So it's not just like a micro benchmark. Theoretically, if you needed 100 servers to serve your application, then now you only need 99. So, hey, that's something, right?
That's a good point. But still, it's only one PR. Let's show these good people another example of using my world-changing tidying method.
What do you say? You want to see another one? All right. That is the type of enthusiasm I am looking for. OK, well, what's our first step?
First, collect the object in one place.
All right, so we're going to use derailed again. Here's our pile of memory. And like before, I started from my top and worked my way down. Let's zoom into this file and see if we can make anything faster. This time, we'll be taking a look at active models timevalue.rb. When we rerun again, we see that a lot of objects are being allocated on line 72, so let's go right there. You'll notice that this method is named fast string to time. Contrary to popular belief, just because you name a method fast, it's not like an optimization thing. Fast underscore 2s. So on line 72, which is what I've highlighted here, we are matching our input string with a constant that is a regular expression. And the reason that this allocates a lot of memory as you can see on 74, is that there are a lot of groupings that are a match. So that $1, $2, $3. And so that is our major allocation here.
Now, does this object allocation spark joy?
Before I can answer that, I have to find out what it does. What does this method do? Reading the method, I can see that a string comes in, and then we are going to return a time object based on this other method called new_time. But can we make it faster? On this line, which is using all of our regex matches, it's not really doing anything. It's just taking those and passing them to the new time method. There's not much to optimize there. But what's going on here? This is $7. We call 2R on it, which makes it a rational float, basically. And then multiply that by 1,000,000 and then call 2I on it. I didn't know exactly what this code did the first time I saw it, and so I ran it to see what the input was and what exactly $7 is. $7 is a string that looks something like this. In that process of calling 2R, multiplying by 1,000,000, and calling 2I, turns it into an integer. So when I look at this, I'm like, well, they're already pretty close. Really, don't we just have to like drop that period? And so that's kind of what I did. We have to add some guard checks, so we have to make sure it starts with a period. We have to make sure that the length is equal to 7, and then we can just strip out that period and directly call 2I on it. Is it faster? Well, in this case, here's a micro benchmark, and it was, in fact, faster. But is there more that we can do with this method? Is there more, if we go back to where we're allocating the regex, can we do more? I mean, I don't think so. So we should probably just...
Don't give up now. You practically know nothing about how this method is used.
Good point. Maybe if we just dug deeper. Maybe if we knew how this method was used, we could avoid it being called in the first place or optimize it some other way. So let's take a look. We're going to add a puts caller. And this is an example of one backtrace that I got from this method. And I'll admit that it took a lot of time of kind of eyes glossed over, looking at this, figuring out what's going on, comparing other backtraces. And so not going to bore you with that just immediately. Let's just jump into the exciting part. The time value method we're optimizing is called, well, generating a cache key. So let's open up that file. This is how we generate a cache key for active record objects. If we follow the stack trace backwards, we see what is happening is that active record is taking a string from the database and converting it into a time object. So that's what our method is doing. That's what that fast toString method is called. And then that is used to generate a cache version. This is where it's called on line 99, so we can go straight there. And conveniently, it's just below where we were looking at. Magic move. OK, here's our culprit. What is happening is that in some database adapters, such as Postgres, the driver returns a string, and then Rails has to cast it. So it does that lazily, so it only does it when you actually use it for the first time. And in a lot of applications, it only ever needs the updated information when it's generating a cache key. And so in this case, it is taking the string, turning it into a time object, and then we're turning right back around and using that to generate another string for the cache version.
Does that mean?
So it means that we might be possibly able to just take the string directly from the database, and this is what we get back from libpq, and here's what it looks like when it comes from the driver, and here's what we need. So if you look really, really closely at this, you might see that if we strip out all of the special characters, we get the exact same format.
Does this allocation bring us joy?
Well, let's take a look. Is it useful? Yes. Caching is a very useful feature. Is it already fast enough? Well, you know, the code creates lots of allocations, so it's slowing us down. Does it help our code to be cleaner? Well, the original code that we're looking at, I would say, yeah, like it's literally just one line. We're grabbing like try, updated that, and it's extremely clean. Is it absolutely necessary? I say no, it isn't. We can directly convert from a string from the database to that cache key without having to do an expensive allocation. So let's take a look at how we can do this differently. Bam. My version of the code is a little bit more complicated. It's got some guard statements, it builds on the existing code, adds some cyclomatic complexity, and adds new methods that have been used that are going to make it maybe a little harder to understand what's going on if you're just looking at it. So no, my version is not cleaner at all. Does that mean that the old code sparks joy? It kind of depends on your judgment. Before we decide, let's look at the performance impact. The patch reduces memory allocations by 5%. Our last patch only reduced memory allocations by about 1%. So it's a lot speedier than the other patch. Is it performant? Yes, I'd say so.
What about performance? How does the 5% translate to speed?
Well, it turns out that every time conversion is extremely CPU intensive, and that my target application, when I turn this on, got about 1.23x faster. That's pretty good. And that's why I said, that memory decrease is a little kind of a proxy. Even better, it's statistically significant. That 1.23x works out to be about 19 fewer servers required to serve your requests.
Wow! That's amazing.
Thank you. Finally, some praise. Well, now we must thank this old code that we have used for many years. Thank you.
You almost forgot something. Every application is unique.
So that's true, and I've kind of glossed over something, which is that this is me optimizing code triage, and then code triage is getting faster. When we talk about benchmarking, we also need to consider different cases. For example, my really big change that I just showed you, I'm like 19 fewer servers, all of you can like spend less on your Heroku bill, which is great, because no, it is. It would be great. I'd love it. But unfortunately, not all database adapters return values in strings. Some have actually already been optimized to do the conversion directly from the driver layer. So MySQL is an example of one that does that. It converts the time objects converts a string to a time object automatically. So Ruby never even sees the string. So in this case, that optimization is actually going to make MySQL users' code go a tiny, tiny little bit slower, which is kind of sad.
That doesn't sound good. Guess your big win isn't for everyone, huh?
Just when I thought I got some positive praise. But the opposite happens as well. If you look at the respond to patch, things got 1.01x faster. But that was just for code triage. Benoit from the RSpec core team used my same patch on their application, which was heavily using Draper, which calls respond to a lot. And they actually saw performance improvements of 1.53x faster. So not only are you writing performance patches, but you are writing performance patches for a bunch of different cases, and they can respond differently. So I'm sure you're excited to try this out and drive it for yourself. So we are going to take a second. Well, sure. Thank you. Thank you for being my hands. Yeah, well, I am pretty comfortable digging around in backtraces, and it requires a good amount of ability to get in and navigate a project, but it's a little harder to do when you can't type. And Caleb here is a fellow Heroku and great handyman, and you said you had an idea.
Enough with the hand puns. So yeah, this is that backtrace that you were looking at before. And you'd said that you'd taken a lot of time looking through each of these lines, and it involved comparing dozens or hundreds of call stacks, like manually. So what if there was a tool that could actually make that a little bit easier? So this is that same set of hundreds of calls to caller, but organized into a tree structure with counts of invocations for each line. You can visually navigate the callers and see that the code calling your fast string to time method changes paths, and you can kind of see that it comes from different places. which can help you to investigate why it's being called in the first place. So that's a pretty complicated tree, so let's take a look at a slightly simpler example of a single test run. The output includes the location, which is the line number and file for each caller. And it includes the frame name, which is usually the method or maybe a block identifier. And this is all so far the same information that you would see in a backtrace. So the same backtrace that you were just looking at, or if you saw an error, this is that same stuff as well. It also includes the number of times that the location occurs in the call stack. So if you had seen this 400 times, then maybe 100 of those would have been from this line. And finally, the symbols are used to visually indicate a tree of the callers and where they're coming from. So you can look at the big picture and find where a method is called most often, and that's usually a good place to start investigating. As you can see here, this one was called twice instead of one time, which is all of the other code branches. So this type of view is also useful for other types of investigation. Say you have a piece of code that you're not sure if you can delete. You've seen it puts when it prints something when you call puts. So you know that it's being used, but you're not really sure from where. And this is a great way to track down where that's coming from. So the tool that does this is a new debugging tool that Richard and I are working on called whence, which means from where. Its API is pretty simple. Wherever you would previously have been doing your tracer round of like 80 bullets, 80 equal signs to find things visually, followed by printing out the callers, you just call whence.whence. And then at the end of your test, print out whence's tree representation. Whence collects the array of callers at each invocation and creates a tree that makes it easier to navigate that call stack. It's still in early development, but you can try it out for yourself now. And that's it.
Wow, wow! That is amazing. So this technique is useful. Let's review.
Yeah, thank you very much, Caleb. So for a review, first, we want to take all of our object allocations and put them in one place and put them in one pile where we can see them. We then next want to consider each. Does it spark joy? Whoop. Finally, keep only the objects that spark joy. So hopefully I've convinced you that object allocation hotspots are a really good indicator of possible performance optimization locations. And now I think you're potentially ready to try these same techniques in your own code or your own library.
私たちの話に来てくれてありがとう。Thank you for coming our talk.
So yes, thank you. My name is Schneeman. This is Caleb, and go forth and allocate less.